Today we'll be looking at working with limits algebraically. Previously we've been using tables and graphs. Here are some specific limit laws that are very helpful and pretty intuitive. For example, the limit as x approaches a of the sum of two functions, you can separate and say the limit of the first function plus the limit of the second function. Same with subtraction. What if you have the limit of a function times a constant? You can actually take the constant outside of the limit and multiply it by the limit of that function. The limit of a product is equal to the limit of each function multiplied. The limit of a quotient is equal to the limit of each function divided. Obviously, the denominator cannot be 0. The limit of a function that is to the power of n can be rewritten as the limit of that function all to the power of n. Same with a root. Use the limit laws and the graphs of f and g in figure 1 to evaluate the following. Okay, the limit as x approaches -2 of f of x plus 5 times g of x. So the limit of a sum, first of all, that was our first limit law, is equal to the limit of the first function plus the limit of the second function. Now g of x is being multiplied by a constant, so we can actually remove the constant from the limit and just multiply it to the limit, okay? So 5 times the limit as x approaches -2 of g of x. So we're going to multiply 5 times that, of course being added still to the limit of f of x as x approaches -2. The limit of f of x as x approaches -2, so f is the pink one, and as you're approaching -2, which is right here, you see -1 is at about 1/2. You're decreasing back to increasing. From the right, it appears to be approaching the f of x value of 1. And also from the left, it is approaching 1. So the limit as f of x x approaches -2 of f of x is going to be 1. And we're going to add that to 5 times the limit of g of x as x approaches -2. So let's take a look at g of x. Okay, that one's pretty obvious. There's no crazy stuff going on, so that would be at -1. The limit of a product of two functions is equal to the limit of the first function times the limit of the second function. The limit of f of x as x approaches 1 as x approaches 1, f of x clearly appears to be approaching 2. The limit of g of x as x approaches 1. From the right side, it's approaching the f of x value of -1. But from the left side, it's approaching -2. If the left and the right hand limits do not line up, if they're not the same, then the limit does not exist. You can't multiply 2 times does not exist, so therefore the limit of this product does not exist because the limit of one of them did not exist. The limit of f of x over g of x as x approaches 2 is equal to the quotient of those limits. The limit of f of x as x approaches 2 is about 1.4, 1.5. The limit of g of x as x approaches 2, spot on, 0. Can't divide by 0. So this limit also does not exist. The limit of f of x cubed as x approaches 1 is the same as the limit as x approaches 1 of f of x, all of it being cubed. What is the limit of f of x as x approaches 1? As x approaches 1, the pink graph appears to be approaching the y value of 2. 2 cubed is 8. Some special units. The limit of a constant as x approaches a is simply that constant. The limit of x as x approaches a is a. The limit of x to the n as x approaches a is a to the n, where n is a positive integer. The limit of nth root x as x approaches a is equal to nth root of a. The limit of, we have some subtraction and addition, so I will separate the limits. I see a constant here with the 2 and a constant being multiplied by the variable here, the 3. So let's bring those to the front of those limits. Looking at the special units that we talked about before, the limit of a constant, no matter what x is approaching, is simply that constant. So the limit of 4 as x approaches 5 is 4. The limit of x as x approaches a is a. So what is the limit of x as x approaches 5? That is 5. The limit of x to the n as x approaches a is equal to a to the n. So in our case of x squared as a, the limit of x squared as x approaches a is equal to a squared. 5 squared. The limit of the polynomial that we started off with, now we've broken down. We no longer need to, once you have used a limit law, you do not need to write the limit symbol, but in every other step you have to write it, okay? It's like getting lazy and not writing plus or minus in front of a square root. You're changing things, okay? You're changing what it means if you don't write this limit notation. So the limit of that polynomial as x approaches 5 is 39. But now you might be thinking to yourself, didn't we just basically plug in 5 for x and we got 39? Like, what was all this craziness, all this work that we had to do? So I started noticing, wait, all the limit laws for some of these functions, I'm literally just plugging in the number and it gives me the limit. But for some of them, it doesn't work that way. Limits by direct substitution. If f is a polynomial or a rational function and a is in the domain of f, then the limit of f of x as x approaches a is equal to the value of f at a. Very interesting. So we can use direct substitution whenever we have a polynomial or a rational function and a must be in the domain of that particular function. Is this a rational function? Yes, it is. Is -2 in the domain of this function? If you plug it in, you don't get undefined, so it is on the domain. All right, we can use direct substitution to find this limit. Again, it's the same as using the limit laws. I'm just expediting the process. -1/11. So direct substitution is a real lovely tool for us. Number 3. What happens if I direct substitute? 1 minus 1, you get 0 on the top. You also get 0 on the bottom. That's undefined. Okay, so we have to get creative for some of these. I noticed that the denominator of number 3 is difference of perfect squares, and that the top is actually a factor of that binomial. So let's factor it out. X minus 1 over x minus 1 is just a special form of the number 1. That would be 1 over x plus 1. Now can we use direct substitution? Yes, we can. And we get 1/2 as our limit. So sometimes we need to do some algebraic maneuvering before evaluating the limit or before being able to use direct substitution or another shortcut. Evaluate the limit of this function as h approaches 0. Again, direct substitution will not work immediately because there's an h on the bottom, and that means dividing by 0, which is undefined. But I do notice that I have a binomial being squared and that 3 is in it. So 3 will eventually be squared, which is 9, and that's a positive 3, and that's going to be a positive 9, and this will be a negative 9. So maybe if I expand this binomial, the 9's will reduce to 0, and every single term will have an h. That way I would no longer have an h in the denominator if I could factor and reduce. Let me show you what I'm talking about. Start by expanding 3 plus h squared. Now every term has an h, and we can factor out that h. Those h's reduced to be 1. The limit as h approaches 0 of h plus 6, now we can use direct substitution. 0 plus 6 is 6. Remember this weird one from Wednesday where we thought the limit was 1/6, but then the closer we zoomed in, the more it looked like it was 0, but the graph was actually inaccurate. We're going to use limit laws now to confirm that 1/6 truly was the limit of this function. First of all, we can't use direct substitution because we have a radical. So this function does not allow us to use direct substitution. We can use limit laws, but we can't use the quotient limit law because then we'll be dividing by 0. We have to do some algebra first. And this is going to sound weird and unnatural to you, but what we're going to do here is actually rationalize the numerator. So we're going to get the root from the top and put it in the bottom. I know, it's counter to everything you've been told. Get the root out of the denominator, get the radical out of the denominator. Now we're going to rationalize the numerator this time. Recall that when you have a radical that is part of an expression that's not under the radical, you have to multiply by its conjugate, which would be whatever you have as your first term, change the sign, and your second term. We will be multiplying by this special form of the number 1. It's to get more stuff in the denominator to help us out. Let's combine like terms on the numerator, and I see that I'll have a t squared over t squared that I'll be able to reduce once I add 9 to negative 9. At this point in time, I can use the quotient property for the limit laws. So I will take the limit of the numerator over the limit of the denominator. That's also the same as the limit of this sum in the denominator. So I'll go ahead and change that. The limit of 1, or a constant as t approaches 0, is simply that constant. The limit of a root is the same as the root of that limit. The limit of a constant as t approaches 0 is simply that constant. Now you can substitute the 0 in for t. So you'll have 1 over the square root of 0 plus 9, which is 9, plus 3. Yes, which confirms what we did on Wednesday, that indeed 1/6 is the limit. The limit of f of x as x approaches a is L if and only if the left-hand limit is L and the right-hand limit is L. Show that the limit as x approaches 0 of absolute value x is 0. The left side of the absolute value function has a negative slope of 1. So when x is less than 0, we follow the line negative x. But when x is greater than 0, we follow the positive line of positive x. The limit of the left-hand piece, so the limit of negative x as x approaches 0 from the left, this right here, is a line, so you can use direct substitution. That would be negative 0, which is just 0. The limit as x approaches 0 from the right side of the right side of the function, which is x. You can also use direct substitution once you have written it as a piecewise function. It's important to note that an absolute value function can always be written as a piecewise function of 2 lines. If the left-hand limit is L and the right-hand limit is L, then the limit is 0. Prove that the limit of absolute value of x over x does not exist. Fun. We're going to use the piecewise function that we did in number 6 to help us. Remember, if we're approaching 0 from the left side, we're going to use the piece of the piecewise function that shows absolute value of x is equal to negative x when x is less than 0. So if we're approaching from the left side, from less than 0, then we can replace this absolute value with negative x because we're only approaching from the left side. This is equal to the limit as x approaches 0 from the left of negative 1. The limit of a constant is just that constant. Now when we're approaching it from the right side, we use the second piece of the piecewise function because now we're looking at the right side, the positive side. This gives us positive 1 the right-hand limit is 1, the left-hand limit is negative 1. Therefore, these 3 little dots mean therefore in mathematics. Therefore, the limit does not exist. Our final example, number 8. Determine whether the limit exists. So for x is less than 4, I use this piece the limit as x approaches 4 from the left, because I'm using the piece that says less than 0. This is a line, so we can use direct substitution. And that would be 0. And as we approach 4 from the right, we use the first part of the piecewise function for x is greater than 4. Which is the same as the root of the limit as x approaches 4 from the right side of x minus 4. Now you can substitute the 4 in, so you have 4 minus 4 under a square root, which is 0. The left-hand limit is 0, the right-hand limit is 0, therefore the limit exists and it is 0.